I would like to welcome you to this DTC RAL presentation seminar and introduce Patrick Skinner, who's visiting us at the Developmental Testbed Center. He's been here for a little over 3 weeks. And I actually want to also give a shout out and a thank you to the person who has actually been his physical host, whereas I've been his host in DTC in name only. So Jamie Wolf, thank you very much for doing a lot to help Patrick get going with this project. And actually John Haley-Gotway, I think, did a lot as well. So Patrick actually grew up here in the Denver area, down in Parker. Went to his undergraduate at the University of Northern Colorado, and then went down to Texas Tech for his master's and PhD, where his dissertation was related to looking at high-res ENKF analyses of internal rear flank downdraft momentum surges in supercells, sampled during Vortex 2. So pretty interesting stuff, in my opinion. And right now he's working at SIMS, which is associated with Oklahoma University, and is working on verification of short-term ensemble forecasts of thunderstorm hazards for the Warn-On Forecast project. And with that, we'll let you get started. And feel free to interrupt with questions. If you do, hang on for 1 second so that I can bring the mic over, because this is being webinared and recorded. Thanks.
Okay, thank you, Tara. Is the mic okay? Does that work? Okay, good. Thank you for that introduction, and thank you to you and DTC for the opportunity to come here and work on this project. So, as you mentioned, I do want to thank Jamie and John Haley-Gotway and Randy Bullock for all of your assistance running MetTools over the past month. Ryan Sobash for many helpful discussions, and then also Adam Clark and Ming Shui back in Norman for actually running the clue. So I had something to look at. And I'm pretty well just throwing together everything I have here, so this is hopefully pretty informal. Feel free to interrupt. I'll provide some brief background. So the data set I'm going to be looking at is a community leveraged unified ensemble. This started in 2016. Adam Clark really spearheaded the effort, and it was more or less an effort to get all the different groups who run convection permitting models together to standardize your domain and grid spacing and different parameterizations so that you could conduct a few controlled experiments. So there were 65 total members run during the spring of 2016, all with 3-kilometer grid spacing over the CONUS grid. And this was done in service of 8 different experiments. So I'm only going to be looking at one of those experiments, experiment 4, and that is looking at the impact of radar assimilation. So there are 2 identical 10-member ensembles I'll be looking at. So I'll say one is SFIS-RAD, which assimilates radar data, and one is SFIS-NORAD. So the radar data, both velocity and reflectivity, are assimilated using the ARPS 30VAR and cloud analysis system. So that actually, I think, incorporates even satellite data and observations of clouds, but radar data is the primary impact on it. And it provides an initial condition of clouds, moisture, precipitation in your model, so you don't have to spin up individual storms or precipitation. So one of the main questions, though, is we know that helps in the very short term, under 6 hours, because you have the initialization of your different storms. However, it's not clear how long that impact extends into resulting forecasts. So I'm particularly interested in looking at periods on the next day. These are all initialized at 0Z. So if you look at like a 24-hour forecast, you get a better representation of thunderstorms the following day when you assimilate radar data the day before. And there are a couple of prior studies that have looked at this, mostly Kane et al. 2010 and Moser et al. 2015. And I want to just draw a couple of differences between what we'll look at here versus what they did. So one is that they looked at deterministic forecasts for a few cases, around 6 to 12, I think. And here we have 24 cases of 10-member ensembles. So we do have a larger data set, so hopefully we aren't susceptible to sort of case-by-case changes in the impact of radar assimilation. We can coax out some of the larger impacts. And the other one is that they looked at QPF verification. And I typically work on the Warn-On Forecast project, where we issue ensemble forecasts of 0 to 3 hours with 5-minute output. So it's sort of backwards from the typical way of moving down to storm scale verification, where you start at mesoscale or synoptic scale verification. I actually got started looking at verification of individual thunderstorms in very short-term forecasts. So I've developed some techniques to try to use observational proxies for verifying these thunderstorm hazards. and I'm interested in seeing how they apply from the next hour problem, which is what Warren Forecast is primarily concerned with, to the next day problem, which is more of the clue time frame. So to give some background on how we'll be looking at verification of severe thunderstorm hazards, this is a difficult problem primarily because you don't have direct observations to verify it against. The full state of thunderstorms is simulated in all the different convection allowing models. However, you only have incomplete observations of the atmosphere. So for example, if you wanted to look at mesocyclone tracks, you have updraft helicity or vertical vorticity in the CAM output you can look at. However, you only have single Doppler radial velocity data to verify that against from the AD network. So you're stuck using proxies such as azimuthal wind shear, which is helpful, but it's subject to different assumptions like solid body rotation, and it's also a derived property, so it's dependent on how well or how clean your radial velocity field is, so you can eliminate spurious objects. And I do want to point out that even when there is a direct comparison between simulations and observations available, that doesn't necessarily mean it's an apples-to-apples comparison. So, can we get the cursor up? Maybe not, I'll just point it out. So on the left here, these are two climatologies from 2016 and 2017 using our NSSL experimental Warren forecast for ensembles. So this is every forecast output from every day from every forecast we issued in 2016, where we used Thomson microphysics. And in 2017, we switched to NSSL 2-moment microphysics. And this is just to state that, the simulated reflectivity is a function of the microphysical parameterization you're using. So you end up with different biases between observations using different microphysical parameterizations. And this would be the same for any microphysical parameterization you use. It's just to illustrate that it is different. So Thomson in composite reflectivity does produce high reflectivities further aloft in the storm. And NSSL 2-moment produces higher ones lower, but it does result in a larger positive bias at extreme grid point percentiles. So the tails here represent the 99.999th percentile. So if you take every grid point from every forecast we issued for the entire year and take the 99.999th percentile value of it, that's what that represents. So these are the extremely high values. And you can get up over 70 in Thomson, and then you definitely, even a low bias in SL2 moment where you're, at 62, 63. And the other thing I want to point out here is that even the verification data set is subject to differences in climatology. So we use gridded MRMS data between the 2 years, and there was some methodology changes in how we interpolated that data and quality assured it over the 2 years, and that actually results in a lower bias in 2017 observations compared to 2016. That's even beyond what you would get from different day-to-day variations. So the point I'm trying to make here is that there's really no way of comparing anything to anything else exactly. So we're going to try to come up with, the best way to identify a threshold and kind of get something that hopefully provides some value. And I just want to mention a couple different strategies for proxy verification. The main one, especially for next day, is Ryan Sobach sort of pioneered this, is a severe surrogate where you take observed storm reports and you spread them, you use a maximum value filter, then you smooth it, and you come up with a probabilistic field of thunderstorm hazard probability in your forecast and then your observations, and you can compare them using neighborhood methods that way. And this is a bit of a different one where you're trying to use the observations, so you'll have more data, which is a positive, and you're not going to be subject to the spatial and temporal errors that you get from storm reports, as well as just sampling error, where you don't always get storm reports where there are intense thunderstorms, and you certainly get over-reporting when it's over a population center, that kind of thing. So that's the advantage of using these radar proxies. They have a significant disadvantage, though, which is that they're noisy. Your radar proxy is only as good as the radar data being put into it. So if it's not significantly quality controlled, then you can end up with more noise than signal in your verification data set and really dramatically impact your verification scores, especially for a sparse field like mesocyclone tracks. So to just provide an example of that, this is the verification data set I'll be using. It's multi-radar, multi-sensor rotation tracks from the WIDSI system at NSSL. And this is an example of rotation tracks from the April 27th, 2011 outbreak. So it's a nice example of what these can provide. You can see, each of the individual mesocyclone tracks across Mississippi, Alabama, up into Tennessee, and so that's a good thing. These are really accurate depictions of where the observed thunderstorms or intense mesocyclones went. However, you also notice that there's, background noise. You have these little splotchy areas which may or may not be representative of actual thunderstorms. So it's a noisy field. And if you don't get rid of a lot of that noise, then your verification stats are pretty hopelessly biased. So that's the challenge, is trying to find a way to clean this up so that you can actually use it. And this is the methodology I've come up with so far. It is far from perfect. I'm hoping that it at least is clean enough to be able to use, but we will see. So from left to right, this is the left is actually the real-time example of the MRMS 3 to 6 kilometer rotation tracks for May 9th, 2016, where we had a tornado outbreak in Oklahoma. This is for 1 hour from 22 to 23 UTC. And it's also thresholded in this case because it requires there to be a tornadic debris signature in polarimetric data, which really gets rid of a lot of values, but not necessarily all the good ones. So you have one good thing. This is the primary tornado of the day, so you do have an indication where the tornado is happening. But lots of these smaller objects there are spurious. That's where you have some sort of correlation coefficient that's giving an erroneous reading of a TDS, and you happen to have azimuthal wind shear co-located, and it makes a rotation track. So if you think about verifying that on a object-by-object basis, you have probably more than half the objects in the domain are spurious. So it's hard to pull out useful data in the stats from that. So what I've done is try to regenerate the rotation tracks and quality assuring the azimuthal wind shear that you use to create them volume by volume. And so this is a methodology I developed for Newsy, and I'm just extending it out to the CONUS here. So this is just the raw azimuthal wind shear that is interpolated to a 3 kilometer grid using a Cressman scheme. And the smoothing from the interpolation, I think, actually helps here because it does smooth out really small objects. So you do require there to be a certain aerial threshold just to have values exceeding whatever threshold you're looking at. And in order to make it into the objective analysis, I require that it has to have input from a minimum number of grid points, so it has to have at least 10 grid points exceeding a certain azimuthal wind shear threshold. And then also you have to have a certain amount of nearby grid points in composite reflectivity exceeding 45 dBz. So it's a very strict reflectivity threshold that's supposed to enforce that you're only interested in azimuthal wind shear when it occurs proximity to an intense thunderstorm. So that should get rid of most spurious objects. It doesn't get rid of everything. We still have problems with interstates, and stratiform rain over wind farms is a particularly nasty one. And once you've done that, then you can apply different thresholds in your object identification. So you can apply an area threshold, you can apply intensity thresholds, and continuity thresholds are one thing that I found really valuable. So you require an object to be there for 15 minutes at 3 different volumes, and that has a good job of getting rid of these really transient signals. And one final thing that's specific to 2016 MRMS data is that they recently discovered a bug in how their azimuthal wind shear is calculated. So this primarily affected regions very near to radars sites. So I'm throwing away data that is more than 180 kilometers from the radar because I assume that at that point your beam broadening is bad enough that you're really not sampling mesocyclones accurately, and it's already going to be well aloft to sample a low-level mesocyclone. But I'm also throwing out data that's within 40 kilometers of an 88D because that's where this error has its largest impact. So in this case, that's a bad thing because this is an actual rotation track from a supercell near Norman that happens to go right near KTLX, and you end up, when you threshold it, it's gone. But I'll apply the same mask to the forecast data sets. So the idea is that you just come up with some verification region where you have data that you can trust. And this is a look at the two regions that we'll be using. So looking mostly the eastern continental United States, I have the 180 kilometer threshold. Can you see the light gray at all there? It's really faded. If you squint, you can see there's light gray areas. That's where the mask is. So only areas outside the gray are considered for verification. And you have one for composite reflectivity, And then you can see all the little polka dots here, which are the WSR88Ds, which are thrown out in the Updraft Helicity verification. So that's the background on how I'm going to try to do this verification. And here's the data set that we'll try to verify. So there are 24 cases from May of 2016. And I just arbitrarily split them into days that I call storm days and no storm days based on whether or not there were 100 local storm reports from the day following initiation. So if there's your 24-hour forecast, there's a supercell outbreak, you get more than 100 severe storm reports, that's a storm day. If not, there are no storm days. And that did cut the data set pretty much in half, so you can compare active days to non-active days. And then I'm going to look at stats for each hour from each member from each case. So try to aggregate everything and look at how the accuracy changes with different forecast hours. And then two primary variables. So general thunderstorm verification, we'll use instantaneous composite reflectivity from each hour and MRMS versus the clue. And then we'll also look at severe thunderstorm verification, and we're going to use updraft helicity. So basically we'll require there to be a mid-level mesocyclone. If there's a mid-level mesocyclone, we'll assume that it's a severe thunderstorm. And in order to do this, we have to identify the thresholds, as we mentioned earlier. So we'll construct these percentile-based climatologies. See, Sobash auto-corrected to SOBs. Of reflectivity and rotation measures and clue and MRMS data sets. So I'm going to step through each of these climatologies now. And this will be consistent throughout. So the SPHYS-RAD ensemble will be orange. The one that doesn't assimilate radar, thank you, will be blue. And so this is just looking at, you aggregate every forecast hour, and then you look at the extreme percentiles in each of the three data sets and plot them against each other. And notice that azimuth wind shear, of course, is a different measure than updraft helicity, so we have a different y-axis there. So actually comparing the values in the MRMS plot in black to the colored plots in SPHYS-RAD and SPHYS-NORAD is not useful, but looking at the different trends in them is the idea here. And one thing that stands out is you have the diurnal cycle in both the radar proxy and then also the different ensembles. However, there's a phase shift in the radar where you have the maximum values during the day actually after 0Z, between 0 and 0.6 UTC. I'm not sure of this yet. I suspect that this is an indication of mesovortices within MCSs. That'll be more prevalent after 0 UTC, and so you have a larger coverage of UH, you have more grid points to sample, and you end up with higher percentile values. As far as comparing the two different ensembles to each other, you can see the spin-up period in the first roughly 6 hours in SPHYS-NORAD, at which point it's caught up to the intensity of SPHYS-RAD. And another thing that is pretty subtle here but stands out is you actually see there is a small positive bias in the members that don't assimilate radar data on day 2. So you'll see in a second, it's more prevalent in reflectivity, but there are some subtle indications that the reflectivity data assimilation is having an impact beyond 6 hours. Another one that's in there is there's a phase shift in the diurnal minimum, where if you assimilate radar data, you actually have the diurnal minimum a little later in the morning than if you don't. So that's the rotation climatology. If you look at the reflectivity climatology, these are the same grid point percentile values. As you get to the very high ones, so 99.975th percentile of all cases, all days, you see there's a really strong positive bias when you don't assimilate radar data on day 2. So here's the first indication that there are differences between the two ensembles that persist beyond the 6-hour spin-up period. And one helpful thing here is that if you look at the MRMS values, they generally follow the same train. There's not as strong a phase shift between reflectivity as there was with updraft helicity. However, the MRMS data are much lower. There's a very strong low bias between the simulations and the MRMS. And there's a good reason for this beyond just differences in how simulated reflectivity is calculated. Did I get that? Oh, I actually forgot to include that slide. But this is interpolated to a 3-kilometer grid. So it's using a Cressman scheme. It does not preserve the amplitude, so you're actually smoothing the data out. I did plot it against the raw, roughly 0.5 kilometer gridded reflectivity data, and there's a constant bias at each forecast hour of roughly 4 to 5 dBz, but the diurnal trend and the changes from hour to hour remain preserved in the smoother data. So another neat thing you can do with the climatologies is just bin different grid points by values and see what the differences are between the data sets. So this is looking at spin up. Blue is SVIS NORAD, orange is SVIS RAD. Gray is MRMS, but because of that negative bias in the smoothed MRMS data, I wouldn't put too much stock in the differences between MRMS and the other two. But what is there is you can see that you have many more grid points. This is a log scale, so order of magnitude more in hour 1, as you'd expect. You're still spinning up storms and SVIS NORAD. But by hour 4, you've more or less caught up, where there's some variation across the different bins of reflectivity, but within 4 hours, you've pretty much spun up storms to match the number of grid points in SVIS RAD and the SVIS NORAD ensemble. And the other one that I wanted to look at there, though, was biases, this positive bias in SVIS NORAD as you get further out into the forecast. So at hour 6, you can see even at the higher 50 plus dBz bins, you're starting to see indications that SVIS NORAD is producing more returns of dBz greater than 50. And that only becomes more pronounced as you go forward. So, at hour 18 is especially pronounced. I mean, in some of the cases, this is a factor of 2 more grid points at 50 plus dBz, which would just be the convective scale. So you're just producing more thunderstorms, it looks like, when you don't assimilate radar data. And this is just to show what this actually looks like in the forecast. So this is a paintball plot. This is a loop of the entire 36-hour forecast. So each member is plotted with a different color when it exceeds 40 dBz. And on the left you have SVIS NORAD, and on the right you have SVIS RAD. I guess that'll be your left is SVIS RAD. And I'll just let it loop through. It's pretty busy. The gray in this case are the observations of greater than 30 dBz to account for that bias. But this is one of the busier days during the period. Tons of thunderstorms in the Midwest. And if you look at one particular instance, so this is 23 UTC, the 23-hour forecast. In SVIS NORAD, you can see you have much larger coverage out into the Midwest, where everything is more concentrated here in SVIS RAD. So, and also you notice that SVIS RAD is subjectively not as accurate. It's missing the primary areas of convection. It does not have a lot in this sort of Kansas City to Iowa, central Iowa area, while SVIS NORAD does. And this is something I want to look at in more detail. If you look through all the individual cases, there's some days where it looks like SVIS NORAD is doing better at 23 hours. There's some days where it looks like SVIS RAD is. But one interesting thing about this was the day before, there was a very strong isolated supercell in northeast Kansas, produced a large tornado near Salina. And it was one of the only storms in the domain. So I'm wondering if the assimilation at 0Z, you put that storm in there in SVIS RAD, and it lays down a big outflow boundary across southern Kansas that concentrates convection on the next day. Now, I have not looked at the environment yet to confirm this, but it's intriguing enough that I think that may be one possibility where you're putting in the 0-hour storms, the day 0 storms in SVIS RAD. You will alter the day 1 environment by putting down outflow boundaries and then removing CAPE and that kind of thing, and air mass overturning. So that's the radar one. And just to look at the same thing now with updraft Helicity. So this is the same loops, same day. And I'd only mention that one nice thing about updraft Helicity is it's a lot more sparse. So you're really not concerned with most of the domain when you look at updraft Helicity, as you shouldn't, because mesocyclones are a pretty small transient phenomena. And if you can look at just sort of the average number of grid points that are plotted here, it's, if you just sort of unfocus your eyes and look at them, they're roughly the same in the two ensembles. So even though you're producing more thunderstorms in SVIS NORAD, it's producing about the same amount of severe thunderstorms. So that's sort of a qualitative look at the different climatologies between the two, and now I'll try to get into some of the Met tools verification of them. So this is just a similar plot to what I showed for New Z. This is to identify the thresholds for verification. So you're plotting extreme percentiles and reflectivity on the right, and then updraft velocity on the left. And the ones we'll mainly look at are these low ones. So you use 40 dBz for clue and actually 10 below that for MRMS. That gives you roughly the same frequency bias between the two. And then similarly for updraft velocity, you'll do 45 meters squared per second squared in the clue, and that corresponds to about 0.005 seconds to the negative 1 azimuthal wind shear in the observed rotation tracks. So this is the first look at actually verifying the different forecasts. So this is fraction skill score with a 165 kilometer neighborhood, so a pretty broad neighborhood, and then intensity thresholds of 40 dBz and 30 dBz in MRMS. So every single forecast pair or forecast for SVIS-RAD is plotted with a little orange dot, which may or may not show up, and then I have box and whisker plots over the top of that. And the first thing that jumps out is the scores are not particularly good. 0.5 plus climatology would be considered skillful. So if we're getting any skill here, some days probably in hours 1 and 2. Generally speaking, and this is consistent with Bill Gallis, who was a visitor here, has also looked at this ensemble, and most of the other verification scores I've seen are finding about the same thing. So we'll be dealing with unskillful forecasts for here on out, but there are some differences in between them that may be interesting. And one thing that is nice is you do get some rise in the day 2. So there's at least some semblance of it picking up towards the end. So that's the SVIS-RAD ensemble, and then these are the corresponding scores for SVIS-NORAD. So there are a couple of dramatic differences. One, which you would expect, is you have just no skill whatsoever at the beginning when there are no storms in the domain, so that's reassuring. However, otherwise, you really don't see much of a diurnal cycle. You see sort of this general 0.3 to 0.4 median value of fraction skill score, and if I toggle between the two, you'll notice that it's a lot higher than the SVIS-RAD for all different times. And if you take the difference between the two and look at the box and whiskers, you're actually getting much higher fraction skill scores in the SVIS-NORAD. However, this is likely a function of frequency bias. So there's different stats we can sort of tease out the impact of that, but I have not run them yet. But my guess is that you have greater coverage, you have greater fortunate hits of grid points between storms. And the last thing I'd mention is that if you look at the difference between the two just for the large storm days, it becomes even more apparent where you're adding the number of observed grid points to match against, and theoretically you have very high frequency bias, so you're actually matching more of them. So that was reflectivity. Let's look at the same things for updraft velocity. So this is SVIS-RAD. One positive aspect is you still are maintaining those first 3 to 4 hours of, reasonably high skill scores. However, you see a lot of variability afterwards, and you don't see a lot of skill, which it's actually a reasonably small neighborhood when you think about trying to verify a 24-hour forecast of an individual thunderstorm. If I run this again, even extending that out to 210, 240 kilometer neighborhood, I might be able to get better matches, because qualitatively, if you look at the paintballs, they're certainly doing well if you think of it in terms of predicting a mesocyclone in western Oklahoma. However, it may be in northwest Oklahoma instead of down on the Red River. But there's SVIS-RAD. Here's SVIS-NORAD. So you see the differences in spin up pretty clearly. However, there's really not a lot of difference. Both are generally bad as you go into day 2. And if you look at the differences between the two, that's borne out. You really have medians right along the zero difference line from after about 6 to 7 hours. And that's consistent with past studies where you find the impact of radar data assimilation helps for that first 6 hours, and then you sort of lose it. And if you look at the storm days, it stays the same as in terms of the median. However, you have a lot more variation because you have a lot more storms. So that's sort of the overview, and unfortunately, that's the only actual quantitative verification I've conducted so far. So I have mode output, and I'm going to look at the diagnostic quantities from that, but I have not gotten the actual object matching scores yet, although I do kind of expect them to follow the same trend. So one thing that's nice about thunderstorms is they really do lend themselves to feature object matching. You can see it in the paintball plots. You have a large number of small transient objects that are sparse within the domain. So if you identify each of these as an object, you can pull bulk diagnostic properties about their area and intensity, compare that to observations, and that's really a powerful tool in terms of identifying where your error is coming from. And you can also use fuzzy logic to match observed objects to forecast objects, which is nice, at which point you can create contingency table measures or even use the different object fields to smooth and conduct different neighborhood verification metrics on that. So that's in the future work category. But for the rest of this, I'm going to look through some of the different mode diagnostic properties for the SFIS-RAD and SFIS-NORAD. This is the object area of reflectivity. And again, this is, I'm kind of fudging the time here just so you can kind of get a sense of where all of the individual objects are distributed. Each one of the orange and blue dots represents the object area of a single object, and then you have box and whisker plots that give you sort of the distribution of it. So you have most of the objects are very small, as you'd expect for a thunderstorm. However, it does get very large. And I draw your attention to the top here, which you probably can't read, but just because I had to truncate the y-axis so you could actually keep the plot readable, I've got the maximum object area for the two different ones plotted there, as well as the total number of objects at each time step. And if you look at the total number of objects, like here's 5,600 for SFIS-RAD versus 10,000 for SFIS-NORAD. 11,000 for SFIS-RAD versus 19,000 for SFIS-NORAD. The maximum size is even more dramatic. You have 4,200 and or so square kilometers for, actually that's only grid points, so it's even larger than that. SFIS-RAD, and for a really large MCS with a large stratiform region, that's not entirely unrealistic. Over SFIS-NORAD, you actually have 21,000 square grid points squared for objects, so you're putting down something over most of a state there. So SFIS-NORAD certainly seems to be producing more reflectivity than it should. And even if you look at just the distribution of the extreme objects, you can see the blue columns a lot more easily. So it's producing, over the course of each case, about 100,000 different more reflectivity objects. You have 240,000 objects in SFIS-RAD and about 330,000 in SFIS-NORAD. So that's the area. If you look at the different intensity measures, so this is the median intensity of every reflectivity object, you don't see a lot of difference here. This is actually, they seem to match up pretty well. You have maybe a little variation during the spin-up period, but certainly as you get out into day two, you see pretty similar distributions. And stepping up to the 75th percentile intensity, you get maybe a hint that the SFIS-RAD is actually higher. And at 90th percentile, you actually have more of a signal that you have stronger maximum reflectivity values or extreme reflectivity values in SFIS-RAD. I'm not sure if I believe this, though. This is also a function of the frequency bias in SFIS-NORAD, where if you have more grid points to choose from, the extreme values are going to occur at a higher percentile. So this may just be a function of there being fewer grid points of extreme or of total fewer objects, to look at in SFIS-RAD. And then this is just looking at the same thing for the storm days, not a lot of difference. So there's the reflectivity, and then I will look at the updraft helicity objects too. And this is my intention for these plots in the future. I made an error when I ran mode for reflectivity, and I did not change the threshold between the forecast and observed objects, so we have almost no observed objects in the database. So that's rerunning now. But at least for updraft helicity, you can look at the MRMS, the actual observed objects too, and get some of the diagnostic properties there. And there's not a whole lot of difference. It's actually pretty standard between the two in updraft helicity area here. If there's any difference you see is during the early morning minimum, you have a lot more objects in your ensemble prediction than you do in observations. So you might be maintaining MCSs longer, or you might just be picking up enough updraft helicity to make it in that doesn't get observed. And then similarly looking at intensity, stepping through from median to 75th percentile to 90th percentile, you see that you don't get a lot of variation. They seem to match up very well. So other than it. One reassuring thing is that there's a reasonably low threshold for updraft helicity compared to other ones. It's good to see that you're actually getting most of the values of pretty significant updraft helicity, which is implying that you're not getting a lot of spurious, very weak updraft helicity objects. You're still identifying mostly objects that have strong values of updraft helicity in them. And similarly for storm days, you don't get a whole lot of difference between them. So it was sort of a race through the end, but that's where I am now. The preliminary conclusion is that there's a strong positive bias in composite reflectivity values and Ensemble members where reflectivity data are not assimilated. So it's in the model climatologies, subjectively in the paintball plots, as well as in the mode diagnostics. And I think this is impacting both the fraction skill scores and then also some of the mode diagnostics in terms of having this very strong frequency bias in composite reflectivity. So, and then otherwise you do see some benefit of radar assimilation in the first 6 hours. That's consistent with prior studies. You don't see a lot of benefit following 6 hours in the updraft helicity, which is also consistent with past studies. And the last one is that there is no discernible bias in updraft helicity objects. So it's implying that the SVIS NORAD is producing more thunderstorms, but the same amount of severe thunderstorms. So the future work will, besides finishing the complete suite of verification products, so the mode object matching is nearly done, and I would like to run mode time domain over the updraft helicity objects because that can give you a sense of errors in storm motion and duration, which I think might be interesting. But then the one thing that I'd really like to explore after this is try to look for some physical reasons for this large bias in when you don't assimilate radar reflectivity. The first thing I'll look at is the environment. Or do you have more grid points of high CAPE, low SIN? Or is it simply a function of putting down different outflow boundaries that help to wash out different regions for thunderstorms that don't occur in the other one? And I'm not sure of what that might be. So if anyone has any ideas, I'd love to hear them. And that's what I've got. So I'm happy to take any questions.
Thank you very much. Thank you very much. Questions? Sure.
So it looks like this talk is more focused on the verification, but I'm trying to understand a little bit more about your CLUE and CAM system. Mm-hmm. And you mentioned 10-member ensemble and doing the 3D VAR assimilation of radar data. Mm-hmm. How did you construct the 10-member ensemble out of 3D VAR analysis?
In this case, I guess I didn't construct it. It was run by CAPS at OU. So they ran several of the sub-ensembles that we're using. And they've been running this for the spring experiment for several years. So there's more information on that, I think. And Ming-Hu has a couple of papers from 2007 that look at that. But there's also something I didn't mention, which is, the method for assimilating radar data could be just as important as whether you assimilate it. So in this case, you have climatological covariances for the 3D VAR cloud analysis, right. And you have different perturbations for the different members, and you're applying the same 3D VAR technique to each member, is how I think it works. But if you were to use, flow-dependent covariances from 4D VAR or ENKF, I wonder if you would get better results or you'd get longer-lasting impact from the radar data. However, that ensemble is not available yet, so I don't think it was for 2017 either. So that's something to look at in the future.
Any other questions?
So you also don't know if the 3D VAR has cycling or it's just one-time assimilation?
I should know this. I believe it's one time, but I'm not sure about that. So I really think it is at 0Z. You take the background from different perturbed guest members, and then you initialize it, run one cycle with 3D VAR plus cloud analysis, and turn the forecast loose.
Yeah, just how you configure the 3D VAR will make a difference in the result. Yeah,
I agree.
Greg looks like he wants to.
Sure.
Yeah.
Your fingers are moving. So, Patrick, I've been down to HWT a number of times. And
right.
I have to say, I've been a little bothered philosophically that we pay so much attention to model-produced updraft helicity. It's like one of the things the forecasters are looking at nonstop out of these clue members, and I'm starting to wonder why, given verification statistics like this. It's pretty poor. So shouldn't we be thinking of other things to be looking at instead? I mean, I'm overall a little dismayed of the forecaster emphasis on model-produced updraft helicity. It's a very overemphasized parameter that's still clearly in need of some significant help.
I agree with you in principle. I'm going to defend updraft helicity a little bit, though. I'll point that I'm actually being pretty stringent in the verification here, where a lot of the work that's been done here by Ryan and Craig Schwartz, and then also by Berkeley Gallo and Adam Clark, where if you take the updraft helicity fields and objects and create a smooth probabilistic field from it, you get something that has comparable skill to a day one severe weather outlook. So here we're enforcing that we're actually, I mean, in a sense, it's almost like a point verification over, you're still applying a neighborhood, but there are certainly ways of taking the different updraft helicity objects and turning it into something that has significant levels of skill. This is, I mean, in a sense, we're applying the Warner forecast sort of paradigm to this next day, and it's really tough to meet.
It's fair. I have to say you're doing a nice job on this. And,
Thank you.
And that spatial constraints you're putting on it are much harsher than most people would consider. So it's a fair statement. Thanks.
And I do want to mention the one thing I completely agree with you on, though, is that, updraft helicity of 50 in one model does not have anything to do with updraft helicity of 50 in another model. So in the HWT, you see these endless swarms of paintball plots of updraft helicity in the different ensembles and the different models. They all use the same threshold. So the subjective skill from ensemble to ensemble is totally dependent on the different model climatologies.
Could you state again why the 50 in one doesn't match 50 in another? I can see the argument for reflectivity, but not so much updraft helicity.
I'll use another newsy example. So we had your scheme in 2016, SSL2 moment in 2017, and performance is generally the same, but you do get different climatologies. So your scheme produces stronger vertical velocities aloft from roughly 4 kilometers to like 7 kilometers than the SSL2 moment. There's a clear bias in vertical velocity, which is integrated over 2 to 5 kilometers to calculate updraft helicity. So even with the same vertical vorticity measures, you end up with different updraft felicities.
That's fair. Careful with the use of bias. You don't know what truth is.
No. Well, yeah, I should just say difference.
On the fraction skill score plots,
Yeah.
are those aggregate values over the entire set of cases? 'Cause
Yes.
there were a lot of dots. It seemed like the number of dots for each individual box plot was much larger than the number of cases. So I was a little confused.
In this case, it's 10 members, 24 cases.
So does the box plot represent the spread among the cases?
It represents.
Because it could be. I mean, that could be misleading in terms of the fraction skill score. If that's looking at among all the cases, it could be overly weighting poor cases when, in an aggregate sense, those cases may not matter as much.
Yes. And one thing I'd like to do is just do a day-to-day. I can plot these end on end for all 24 days and just see, or for even 31 days with the gaps over weekends, and sort of get a sense of what the spread is case to case. Because you're right, this has got mix between spread across different ensemble members and different cases, and they're all sort of crunched into one plot.
Any other questions? Well, I have one question, which is you were stating that you really didn't see much difference between the phys-rad and the phys-no-rad in updraft helicity, but when I was looking at between 0 and 3 hours, the distribution, the box plots actually looked like the no-rad, I can't remember which way, it wasn't neighborhood, I'm sorry, it was looking at the mode objects, I think. It looked like the no-rad was higher. Go further. One more. Yeah, like there.
Oh, yeah. And actually, you're right. And I think that is indicative of, in the climatologies, so I'll go all the way back. Where are we at? I'm trying to think. Yeah, it's actually, I remembered it being a little bit stronger than that. I was actually thinking of the reflectivity, where you actually, once you get spin up in the NORAD, you actually get, this between 6Z and 9Z, you sort of get this big flare up of thunderstorms. And I wonder if there's actually a little, there's maybe a little subtle evidence that you have a positive bias at the extreme values of Updraft Helicity. But it was in the mode diagnostics too, so.
All right. Any last questions? All right. Well, then let's thank Pat once again. He will be here through tomorrow afternoon if anybody still wants to go find him. He's over in FL3, and otherwise he'll be finishing up his visitor project in the next 6 months or so. Yeah, and be putting together a report that we'll have up on our website. Thank you very much.